Thanks, Ephraim. So it's a real pleasure to be here. I have a very fond attachment to this university. Even wandering around the streets, I remember all the buildings and nooks and crannies of it. And it's also a pleasure talking to you because you're a very knowledgeable audience in this field, and I'm going to try and draw your attention to what I think is an exciting new direction for manipulating light, that both in the quantum regime and also in the classical regime. And so the focus of this talk, or sort of the loose thread that's going to go through this whole talk, is that in this talk I'm going to focus on trying to manipulate photons via their transverse momentum. And in particular, we're going to try and create general optical transformations. And also tell you what those are, and I'll sort of go into more detail about that. Sort of a shorter, more pithy title for the talk that I could have given was Spatial Frequency Light Modulation. So that's sort of a play on the fact that we already have spatial light modulators. Wouldn't it be nice to have spatial frequency light modulators? But that kind of reminded me that I should probably take a step back and just say what I mean by momentum, spatial frequency, and so on, because there's a lot of different terms that can be applied to this, basically the same idea, particularly if you're dealing with monochromatic light. So here we've got momentum, we've got spatial frequency. So generally light is described by a superposition of plane waves, and you can think about one of those plane waves is coming at some direction with some wave vector k, and then the momentum is just h bar k. So there's going to be a momentum in the transverse momentum component in the transverse direction. So that's the momentum that I'm talking about up here, not the full momentum. And then of course k is 2 pi over lambda. So lambda is setting a length in space, which is analogous to period in time or a frequency. So 1 over lambda is like the spatial frequency, and that's just a terminology that mostly comes out of electrical engineering. So spatial frequency is talking about the transverse k is talking about transverse momentum, and then lastly, the other thing that's also synonymous if you're dealing with monochromatic light is just the angle. So all 4 of those concepts are really the same thing. And unfortunately, I try to stick with momentum throughout this talk, but I might change a little bit accidentally throughout it. So I'm from the University of Ottawa. I'm in the physics department there, and I lead an experimental group. I'm also, so you guys have your quantum institute. We have a new quantum institute called the Nexus for Quantum Technologies. And I'm also part, well, I'll tell you in a second, I'm part of a joint center with NRC. And we also have a Max Planck Center that's in collaboration with the Max Planck Institute for the Science of Light in Erlangen and the Max Planck Institute for Quantum Optics in Garching. So we have lots of exchanges between them and us. So sometimes you have to click. Uh-oh. Now I'm worried about, I'm going to get this to go forward. What if I click? Oh, it worked. Good. Okay, good. Yeah, sometimes you have to click to get its focus back. Oh, but now I've got the screen controls again. Okay, can never win. Yeah, but you'll probably, okay. Yeah, well, you can try it, but it might stop me from advancing. So this is where I am in Ottawa. This is our building that was on the first slide, the ARC building. It's right in the center of Ottawa, basically a block from the canal. You know, the canal's kind of famous because it freezes and you can skate on it. So we're right in the center. We can walk to the apartment buildings. This is a kind of old picture of my lab. I don't have a new picture because I've made these all into U-shaped tables, so it's hard to get a view down the lab. So that's what it looks like there. And this building is about 8 years old, and it was purpose-built for optics. Our labs are on these tables of concrete that are over nothing on metal piles that go down to the bedrock. Totally overkill for what I want to do, but it's nice to know that you're not going to have vibrations in the building affecting you. More recently, I've started up another lab that's basically very similar looking to the lab at University of Ottawa, but it's really aiming at connecting quantum pieces of technology at different parts of the optical spectrum, or even even all the way out into the microwave potentially. So this is an actual room at the National Research Council, which is just on the same street as our building, but just at the other end, about a half-hour walk. That's the Stacy Institute, the first building of the National Research Council, and that's the building that my lab's in. And it's a collaborative lab with two people from NRC, Ben Sussman and Kabat Hashami, and then Ibrahim Karimi is another professor at the University of Ottawa, and myself. And if you've been there, you might have visited, you know, so this is the building right there that I just showed you. And then there's the waterfalls right beside it, and you can go to this nice cafe when it's summertime, which is only a small fraction of the year, unfortunately, but in the summertime, you can go to a nice cafe overlooking it right next to the falls. And you can, the nice thing about Ottawa is that the outdoors are very accessible. So this is Gatineau Park. You can literally bike to lakes and go swimming and canoeing and so on. So that's sort of to convince you to come and join our group. So these are the people that are involved in this. I'm putting them at the front of the talk so I don't rush through it too much. It's been the topics sort of span a few generations of graduate students and postdocs, including Lambert Ginet, who's now at the University of Moncton. And in particular, it was a collaboration with Bob Boyd. Some of the stuff was a collaboration with Bob Boyd and Orad Reshev. Orad's now in private industry, but he was a postdoc. And some of the later stuff is a collaboration with Francesco Monteconi and his student Kunal Shastri at Cornell. Okay, so I'm going to tell you about momentum transformations, but the reason why it's interesting is because most of the transformations that we do on spatial light fields, spatially distributed light fields, are based on manipulating the position, the light at particular positions. So consider a lens, right? Most of you know that you can turn a lens into just a phase profile that applies a phase at each position in the lens. And if you make that phase profile correct, that thing, which we might call Fresnel lens or a meta lens, will do the same thing as this glass lens here. So it would focus light. And this is really taken off in the area of metasurfaces, because here you don't actually have to make sort of thicknesses of material to create your phase shift. You can create little antennas and so on to create the phase shifts at any point. But to be honest, even Fresnel lenses are still big technology. So you can, if you get your cornea, or no, your lens replaced, in your eye, you'll have an option to get a Fresnel lens on top of the replacement lens to do additional correction and to increase your depth of field and so on. So you can get a Fresnel lens implanted in your eye, and it's very common nowadays. But in fact, it's not just lenses. Most of the optics you can think of manipulate light based on its position, including diffraction gratings, because again, this is in some sense a diffraction grating, right? You're just changing the phase as a function of position, and all sorts of different optical metasurfaces, which are a hot topic. So the most general thing you can think of to manipulate light based on its position is a spatial light modulator. So a spatial light modulator is just an array of liquid crystals, each of which you can control the birefringence of, or the phase that it applies to light, by applying a voltage. And the voltage just causes the liquid crystals to turn, which changes their index. And so you apply a phase, and you can control the voltage at each pixel. And by doing that, you can apply a phase that gets transmitted through this array of liquid crystals. And that phase can be different at each pixel. So here you can make any phase pattern that you want, any phase mask you want. So you can make lenses, you can make diffraction gratings, whatever you want. They're kind of remarkable in the context of control because they have millions of pixels. There's very few things in optics where we have millions of degrees of freedom of control. Ideally, they would be all transmission. It would be much easier to use them, but they work better if they're reflections. So in practice, almost everybody tends to use reflection models. Okay, so that's the spatial light modulator, and I have like 5 of them in my lab. They're very common nowadays, and there's lots of people who specialize in making optical transformations with them, like making Laguerre-Gauss modes, donut beams, and Bessel beams, and all sorts of crazy states of light, spatial states of light. And if you talk to that community, there's sometimes a misconception that these spatial light modulators can do anything. They can create any transformation. And because they are so powerful. So I wanted to just illustrate a counterexample of where you can't make any transformation with such a device. And it goes back to the two regimes of diffraction. So there's one regime of diffraction called Raman-Noth diffraction, where you have a thin diffraction grating, and you have a beam coming in. And essentially this diffraction grating is associated with a K vector to do with the period of the phase modulation. And that K vector will give your light a kick in both directions. So it can make it go down, or it can make it go up, or it could leave it alone. So thin gratings can create this diffraction. So that's what a single SLM can do, because the index, the thickness of those pixels is very thin. They're on the order of microns. On the other hand, if you have a thick grating, then you can get Bragg diffraction. And you notice that in Bragg diffraction, you have a beam coming in, and it only creates two modes coming out. So the mode that goes straight through and the diffracted mode, right? It, in fact, couples these two modes. So here we had three modes, and here we had two. But more importantly, is if you wanted to take one of those modes and send it back through that grating, right? So one of those diffracted modes, say you wanted to stay in the space of three modes. Well, that's not going to happen, because every time you go through, you get a new momentum kick. So you're going to create another new angle. So your space of states is just continuously increasing the number of times you go through this device. So your Hilbert space dimension is just going to keep growing. Whereas in Bragg diffraction, if you come in with one of those diffracted beams, you again just diffract into those two. So your space is limited. Oh, you're bad. Oh, geez. That's not good. So in Bragg diffraction, you can create transformations that will couple these two states, these two different directions of light. And so you can create 2x2 transformations. Transformations are analogous to what a beam splitter would do. Whereas here you can't. There's just no way of limiting your Hilbert space with a single plane. I don't even know. Should I wait, or I'm not sure I can advance until we. Okay. Okay, so that's sort of the motivation for the talk. There's this missing thing. We can't make all transformations for light, including even that Bragg diffraction. We can't even just make a 2x2 transformation with spatial light modulators, even though they're really great. So I'm going to go through some context, which is what has been done for making general transformations, which we call universal transformations. In the context of quantum theory, we would call those unitary transformations. So this in sense is a universal way of making an arbitrary unitary matrix. Then I'm going to so this is one way of doing it. Then I'm going to tell you about another way of doing it that could have some advantages, where you're doing momentum modulation. Is it okay? And then I'm going to tell you, so this is the advantage of doing momentum modulation and being able to do universal transformations. And then I'm going to tell you about ways of doing more direct momentum modulation and what that would let you do, including making something called a space plate, which is a thin plate that replaces a larger region of space. So it could be useful for imaging. And then later, we're going to explore, at the very end of the talk, which is where I'll probably run out of time, we're going to explore many different ways of doing this direct momentum modulation of light, including creating various types of metamaterials. Okay, so let's start off with saying, what is a universal unitary? So for two beams coming in, a universal unitary is something that probably a lot of people in optics are very familiar with. It's just a beam splitter, basically. So if you have a beam splitter with a variable transmittivity, and then you have a phase that you can control, or that's in your beam splitter already, before and after, and then a universal phase, that is a parametrization of a general 2x2 unitary matrix. So this is the most general matrix that you could write down to manipulate a two-dimensional quantum state. And in this case, it's these two beams, but it's the same type of matrix if you're talking about polarization, because polarization also has two states, and so it's going to have the same number of parameters in its unitary matrix. And I should say there are for n states, there's going to be n squared free parameters in your unitary matrix. The one we neglect quite almost universally in polarization is this one, which is like a overall phase, but it does come up in geometric phase. So this is how you'd make a general unitary for just a 2x2 state. What about bigger beam arrays? Well, this was introduced by Reck and Zeilinger way back in 1994, where they showed how you could combine variable beam splitters with variable phase shifters to create a universal unitary now on n beams coming in. So you'd have a photon, say in the language of quantum optics for single photons, you have a photon that's in a superposition of being in these n beams. It's in one of those n beams, or a superposition. Each state represents a photon in one of those beams. And then coming out, you have a new state, which is just going to have new coefficients, but you can represent that as this unitary that you're trying to dial in times that state. So you can see here that this is a way, this is a mirror. So you have these beams coming in, and then they reflect, which causes them to cross, which gives you convenient places to put these beam splitters. So those phases and those reflectivities, if you count them up, you get n squared parameters, and that lets you dial in any unitary. It's a really brilliant idea, and it turns out it's been highly influential, but it took a long time for people to actually build one. And I know they wanted to build this in the Zeilinger group, and they tried to build it for quite a few years. It's just very hard to make something like this in free space. You're basically building, I'm not quite sure, n squared probably, or n interferometers here that all have to be phase stable. And so it's very, very difficult to do. So that was in 1994. And it took until 2015 for somebody to actually finally implement this. And it was Jeremy O'Brien and Anthony Lang, and lead author was Jacques Carolin from Bristol. And they did it, the way they did it is not in free space, but in integrated optics. And the other thing they did is they replaced their variable transmittivity beam splitters with Mach-Zenders. So if you have a Mach-Zender and you vary the phase inside a Mach-Zender, you can change where the light goes at the output port. So that variable transmittivity beam splitter can just be replaced by yet another interferometer. And inside that interferometer, you're just varying a phase. So now you're just varying phase everywhere. You're no longer varying the transmittivity. So this was, as I said, this was highly influential in the field of quantum optics, because with this one device, you could now dial in any quantum optical setup that you wanted. The only thing that varies then is what light you put in and what detection you do at the end. So they used this in quick succession to demonstrate how to make C0 gates, how to do random walks, and quantum information processing was random walks. It's been used to do boson sampling and so on. And if you go and look at optical quantum computing companies, this is what they're doing. This is what all of them are doing, something like this. So as I said, it's been highly influential. So people have made various versions of it. You can see that these are all metal pads for the electrical control. You can see that you're starting to fill up how much electrical control you can do there, because you have to control all those different phase shifters. People have done things like do quantum transport simulations. They've done these in 3D by laser writing them, so not just sticking to a plane. They've made them modular, so you make, now remember, there's replacing the variable transmittivity beam splitter by Mach-Zenders. So this is our Mach-Zender right here, and that's now a 50-50 beam splitter that's fixed. And now these are the phase shifters. And so now you can just think of this as layers. And you can make a chip with just a single or two layers, and then bring another chip in and make it exactly the same way, and you can just attach them together. So you can make a circuit that as long as you want. Kind of simplifies some of the fabrication. And in particular, it hasn't just been influential in quantum optics, it's actually probably been more influential in classical optics. So it's interesting that this is an idea that came from the Zeilinger group, but now it is there's many different classical optics companies that are based on this idea. And that's because, again, you're making a completely changeable, arbitrary optical circuit on your chips. So you can basically make whatever you want, right? After you've made it, you can decide what it's going to be. And one of the things that, as you probably know, that's a hot topic is machine learning. And it turns out that computers are already being sort of challenged by the computing demands of machine learning. And part of that is after you've done your learning and you've figured out your network that you're trying to make, there's a bunch of matrix multiplication that you need to do to apply that machine learning to something like coming up with a new image or something like that. And it turns out that a unitary is just a matrix, right? So if you just put these in a row, then you're effectively multiplying those unitary matrices. And then there's also, I don't have time, but there's a generalization of this, a small change that has to do with the singular value decomposition, which doesn't frees you from being limited to unitary matrices, which of course are square, to general matrices that can have any shape. So there are now a couple companies that are based on this, and they actually have commercial products that you can buy. So you can actually buy one of these chips and put it into your computer at this moment for doing.
When you say 6 times faster than Moore's law, you mean the exponent is 6 times?
Oh God, I wrote this so long ago. I really have no idea what exactly. It was from one of their slides, so I'd have to go dig up one of their slides. But it was this singularity that we're heading towards in terms of the requirements of machine learning. Okay, so yeah, so it's very popular in classical optics. So I'm not doing that. Well, I am kind of doing that in my lab, but I'm not going to tell you about that. I'm going to tell you about a different way of doing things that is in some ways more approachable for your average experimentalist. And again, it's going back to this momentum control. And it gets around some of the challenges of these chips. So one of the problems with these chips is that you need a massive amount of control for them. You need to control n² phase shifts, which quite often are made from heaters. And then you have heat that's spreading, so you have potentially crosstalk and so on. So there's a lot of issues in terms of controlling these chips that are very challenging, and in particular doing it fast enough so they can compete with regular chips. So one thing, as I said, that has a lot of control already built in that we can just buy commercially, every one of us, is a spatial light modulator because it has millions of pixels. But it only does these phase shifts in position space, so it can't do these arbitrary transformations. And the thing that we're missing here is we need to mix the light at 2 different pixels. So those beam splitters were doing that before. Oop. Right, just one more thing there. So those beam splitters were doing that before, and then they were interleaved with these beam splitters, or these phase shifters. Sorry. So we have layers of beam splitters followed by layers interleaved with layers of phase shifters. The beam splitters were mixing, and then the phase shifters were sort of dialing in the unitary. Or you can see it here more clearly. You have your phase shifter, and then your beam splitter, and your phase shifter, and your beam splitter. So instead, we're gonna use a Fourier transform as our mixing element. And in the context of optics and space, a Fourier transform means that you're going from position space to momentum space. So we're going to do mix with a Fourier transform, do a layer of phase shifters, mix again with a Fourier transform. So a Fourier transform mixes because if you send in light here, a Fourier transform will send it into a flat distribution of all the output modes. So it's the best mixer, right? It sends one thing to everything, whereas this sends one thing to the neighboring. And so we could do this in an optics lab with a lens. A lens takes a Fourier transform of the spatial distribution of light or a curved mirror. And so we would come in and manipulate with a spatial light modulator in X, use a lens, and then do P. And it turns out, so, I mean, the question is that enough? I mean, it seems like it could be enough, but is it enough? Well, it was proven all the way back in 1981 in terms of a discrete space, a DFT, that you can decompose any unitary matrix into this interleaved diagonal matrices of phase shifters and then these DFT matrices. So this was proven a long time ago, but it was an existence proof. So
is there bound on how many you need in the sequence? It's not just one pair, but
So it is unknown.
Okay, so
Yeah.
there's some terminating.
So that's what I mean is that there was an existence proof that shows it is it's an existence, it's a constructive existence proof, but the overhead is so large that I can't even remember it. It's not relevant really. Nobody would ever do it that way. So we don't know how many layers you need to do this, right? But at least we know, at least in principle, it's possible to do this. And then so since we don't really have this theory behind this analytical minimalist theory behind it, we still have to come up with these phases and try this out. So how do you do that? Well, this was really an invention of a group in Australia led by Joel Carpenter, and he took an idea from integrated optics, where what you do is you take all the states, all the basis states you're sending in, and then you look at what you want in the new basis that you get at the end, because a unitary transformation is just a rotation. And then you just think about these phase planes, and you just fix the phase to compensate only the phase difference at that plane between the input modes and the output modes. So you're not really doing anything to try and change the amplitudes. You're just doing it, and you have to do it iteratively. So it's an optimization. It's not even proven that it's going to work. Nobody really knows that this should work. They just tried it and it did work. So they did this and they came up with devices where you interleave back and forth that could do sort of interesting transformations. So that's called wavefront matching. But even before Fontaine did this, there was a group at LKB in Paris that also showed how to do this, and there they were using this curved mirror that I was telling you about. So you come in, you do this SLM that puts a phase on your beam. So there's many different pixels across that. You reflect. You now are in momentum space. So now position here is what momentum was over there. You have an array of pixels that phase shift and so on. You just keep on reflecting over and over again. So here's an example of what happens to their transformation. So here they're not trying to do a universal unitary, they're just trying to make a transformation. And what they want to do is they want to come in with one beam and end up with 3 Gaussian beams. And you can kind of see like what happens to the field inside. So there's phase planes here. And what happens to the phase inside. And it's kind of random, which is kind of what you expect from, it's not easily understandable, which is kind of what you expect from an optimization. Like you could call that machine learning in some sense. And machine learning is kind of famous for coming up with inscrutable implementations of things. So they actually even have a commercial a company that has a commercial device now that you can buy this, and it's really just focused at this. It's focused on, say, taking a Gaussian mode and making a Laguerre-Gauss mode. And that's for optical telecommunications, because you can pack more information into a single fiber if you use other spatial modes of light. But what was really surprising was Fontaine, these people that came up with this wavefront matching, tried this as well, and they managed to make a transformation that involved 210 different modes. So that would be our N for our space. And if you think about that, that now requires 210 squared degrees of freedom. So it's quite large. And naively, if you think about that, this method of interleaving the DFT with the phase, you'd think that you need N planes. I'll explain in a second why you'd think you need N planes to do this, at least in the minimum. It's just counting degrees of freedom, really. But they managed to do this transformation in 7 planes. So here you'd think you'd need 210 planes, and somehow they get it to work in 7. We don't know why. They don't know why either. It just did. And so it was kind of a surprise that they could get something working so well. And so, this of course bugged me. Why I like having analytical answers for things about how many planes we need and so on.
Just that they've chosen a very simple transformation. They're not trying to do a general transformation.
That's right. They're not doing a general transformation. They've picked a certain transformation. But did they get lucky with this transformation that it needed less planes?
Right basis, you can do it in one plane, right? So
exactly. But what makes this the right basis? That kind of question. Those kind of questions, and literally there are no answers. Nobody has answers for those right now. So I did work on this a little bit with Florian Marquardt at at the Max Planck Institute for the Science of Light. And we managed to get the constructive proof. Well, we didn't even start with that, but we managed to come up with an analytical design for this that where you could actually come up with it's not really a formula, but at least a deterministic procedure to come up with these phase planes. But it's still not minimal. So it's not really in itself particularly usable, because it ended up with at least a factor of 6 overhead in terms of the number of phase planes you need, compared to what I think is the minimum, which is just n. So we came up with that. So it's published if you ever want to look at it. And hopefully somebody can take that and maybe push it further and find an even more minimal solution. Just want to briefly mention that one of the surprises when we did that paper was first of all, we were doing things mathematically. So we didn't want to deal with the Fourier transform. We wanted to deal with the DFT. It's much easier to do this matrix algebra with. And so we assumed that in integrated optics, people knew how to do DFTs. And if you look, there are many papers where they say they're doing a DFT, but they're really not. They're just scattering one mode into all the other modes, which is not the same thing as a DFT, because you have to have the right phases as well. So we invented a way of doing a DFT, which is a lot like how a Fourier transform works, in a sense that you just create a big box with high sides that ideally would reflect all the light. And then you have a number of modes coming in. And what happens is you get sort of self-imaging of the modes at particular points. And at those self-imaging, I think it's half the distance between where you go back to an image of itself, you get the DFT, it turns out. Just my idea was Victor's, and he just had an intuition that this would work, and he worked it out, and it did work. So this is a design that I'd like to pursue sometime, of trying to make this and seeing that it works. But that's it. We don't use it, and that's all that we did with that theory. Okay.
Sorry,
Yeah.
If I just send light into one mode, nothing is going to constrain it to only be on those discrete points, right? So this would be a very lossy discrete.
If you send in light here, then at these points, the light will match the modes of the outcoming. It's the boundary conditions that on either side that cause this to happen.
What here defines the number 6? How does that point at A know that it could turn into 6 spots?
It's the sides of the width of the and the spacing of the waveguides.
I know about the spacing. I come in A.
Because you're coming in at a particular point, and then imagine just you have standing waves, right? Those are going to define the spacing here. That's independent of A. So you have to choose the spacing to match something to do with the width of the waveguide, and you also have to choose the length as well to be the correct length, which is half of the full self-imaging length.
So then there are other lengths at which I'll get any other integer number of points. It doesn't seem plausible to me that if you have one input and put it into a rectangular waveguide, you get discrete points with arbitrary numbers of integers.
Well, there's a wavelength here. So we're assuming, there's something so when I was talking about the standing wave, you're assuming monochromatic light. So there is a number that's being defined by the ratio of the wavelengths to the width. So there is a special number to do with the structure. It's not arbitrary.
Okay.
Okay. So yeah, so we'd like to make that one day, but in the meantime, we're just doing this much like the LKB lab did and Fontaine did. We're going to go back and forth, but instead of focusing on transforming into Laguerre modes, we're going to focus on doing these universal unitary transformations. And for the purposes of quantum information processing, let's go back to this beam state, which has some advantages even in terms of control, because if you think about a spatial light modulator, it's square, right? So if you have a certain number of pixels along this direction, if you step down in some ways and ideally you'd be using each row of pixels as a different reflection, you're kind of maximizing your use of those degrees of freedom. So in the extreme case, if you had one spot for every pixel, right? And you had 100 pixels, you could do 100 modes as long as you had 100 layers going back and forth. We have not been able to get close to that. Okay, and just to be clear, what I mean is just that you have a photon that could be in this state, and you have some complex amplitude, or it could be in that state, some complex amplitude. So this is what it would end up looking like. You end up reflecting back and forth. And these are the actual phase patterns that we put onto the SLM. Again, you look at them and they don't have there's not a lot of intuition about why they are the way they are, because we use this wavefront matching algorithm, because we don't have a good minimalistic deterministic algorithm to do it. This is just some preliminary work testing how many times we could reflect off the SLM itself. It was about 10 times is the maximum we could figure out. It's mostly limited by like the casings of things. So sort of some geometry that you could probably think about improving if you wanted to. And this is just to give you these were actually some old results, some preliminary results that we got. So if we sent in one mode, we could make a superposition at the output. So we started off with we've so far only done actually 2 beams coming in. So in the future, we'll increase it. And this is just showing that we could do that beam splitter transformation. And this sort of shows you what the light's doing as you go through. And again, it's just transforming in kind of a random, non-intuitive way. But we wanted to really explore the space of all unitaries. And remember, there's all these 4 parameters in it, one of which is a global phase. We're not interested in that. And there's another phase in there that's kind of trivial because it's just phase shifting one of the outputs. So in the end, we were left with just 2 sort of non-trivial parameters that we wanted to play with. And so one is effectively the mixing of the beam splitter, and the other one's a phase shift at the input. And then we looked at how well we could make all of those unitaries. So we characterized the state coming out, and we looked at the gate fidelity. And so this is our plot. Just keep in mind that this scale of the gate fidelity goes from perfect to like 90.93. So even though there's some black there, all of this is pretty good. So it seems to work pretty well for this two beam case. And now we'd like to push it up to more beams and then potentially put in quantum states. Yep.
Am I reading the plot right in that 0, 0 should be identity?
Yeah, I think so. 0, either 0, 0 or the other side. I'd have to remember. Yeah.
Identity being worse than the corner.
Okay, so one thing is that the modes coming out to get this to work really well, the modes coming out are actually a different width than the modes coming in. We don't know why that is, because we're using this wavefront optimization. So no matter what, even when you're doing the identity, you're putting on phase masks, and those are going to be associated with imperfections and so on. Essentially, those phase masks in the identity case are just going to be those of lenses to sort of refocus your beam. So I think that's why. Okay, so I'm going to run out of, I guess I have a little bit more time, but I'm going to run out of time. But so briefly, I just want to tell you about an idea that came up while we were doing that experiment. And that is, right in that experiment, we were reflecting back and forth between this mirror, and we're taking this Fourier transform every time. And we thought, well, this is kind of annoying because effectively we're always still doing this phase shift in position space, right? Even though we're converting back and forth in some ways, we have to use this curved mirror to go back and forth. What if we could manipulate K directly, right? What if we could come up with some sort of device? I didn't even know if that was possible. And if you do that, then you can start thinking about even more general transformations, not just like of beam arrays, but transformations that you might use in imaging, because any light field can be decomposed into a sum of plane waves. And so if you manipulate the K there, you could manipulate your entire light field for the purposes of imaging. Okay, and then we said, well, what would be the simplest target for a transformation that we could do? And we had said, well, from my days learning about Fourier optics, probably the easiest thing we could aim for was just the transformation that free space propagation implements. Because as you travel through free space at an angle, you pick up phase, and that's it. You don't get attenuation. Sounds really easy. Remember, angle is K, so you have a K-dependent phase. What exactly is that phase? It's actually kind of unintuitive, what that phase is, but it's essentially your KZ component times the distance that you propagate through, and then you can just write that in terms of your transverse component by Pythagorean theorem, or you could write it in terms of your angle. So in the language of Fourier optics, the transfer function that we're aiming for is this. We want to apply this phase of the functions of Kx. So we call that a space plate. And after we came up with that idea, we kind of realized, hey, that space plate would look very strange if we made it. Because essentially what you'd be doing is taking some region of space and its effect on your light and compressing it into a thin plate. So imagine a beam coming in through this region of space. It would exit at a different point, but at the same angle. So now if you make a thin plate that does that, you'd have a beam that comes in and it somehow magically moves over and exits at the same angle. It's a very strange, it seemed like it would be a very strange thing to observe. We characterized how well this would work just by the ratio of the two spaces, this R. And of course, this would be useful for all sorts of things, because if you can compress free space propagation into a narrow distance, you could make ultra thin cameras, because your cameras, the sensor is flat. You can make flat lenses, so now you can make the whole thing flat. You could solar concentrators, you could potentially replace the space between the lens. Even spectrometers have used free space propagation, and even integrated optics, like that DFT thing I showed you, is using propagation. So you could replace that propagation with potentially the space plate idea. But is it even possible? So we don't know if this is possible. We need a phase that depends on angle. And our first idea was just to say, what if we just had an index that depended on angle? What index would you need, right? And it turns out there's a whole family of indices. So this is your K vector inside the medium. And then this is the index. And there's a whole family of curves that would implement the right thing that you need for free space propagation. There's a family because you don't care about the global phase that comes out. And of that, I noticed this curve here, which to me looked like what you get from a uniaxial crystal. I just somehow remembered that. And so then I went back and looked at the index that you get from a birefringent uniaxial crystal. So now you have two indices in two different directions inside this material. So as you change your angle, you're getting a combination of those indices. And so we recognize that this was a negative uniaxial crystal, which means that, for those of you in optics, means that NO is larger than NE, and the compression you would get was just the ratio of the two indices in the crystal. But you need to, it only actually replaces space if you put it in a medium, it's replacing space in that medium that matches this NE index. It's not as good as replacing free space. So we wanted to try this. And so we wanted to see if it would actually work for imaging. So we put this in. So it's also a weird arrangement because your axis is along your propagation direction. It's not how we usually use uniaxial crystals. And we wanted to see if it would work. So what we did is we put a uniaxial crystal, calcite, into a matching medium that matched its extraordinary index. So that medium was glycerol. And then we imaged just a printed stamp, or a painting, actually, a printed painting, through that. And then we just took it in and out and saw whether it moved that image closer and shortened your system. So let's see if I, whoop, geez. Okay, let's get that. Okay, so we're moving, what we did is we moved this camera back to see where the image was forming. And my animation is not working. Okay, I guess this is the drawback of copying. It's a really great animation. And then now you can see it not working again.
Sometimes the TikTok below, I see ones that.
Well, that's why I wanted to put it on the desktop. I don't know. Okay.
Yeah.
Okay, well, yeah. So you can imagine as you're moving this camera back, you see this full color sharp image focus closer to the lens when the calcite crystal is in there than without. And then we also want to look at this walk-off to see if we tilted this plate, if we came in at an angle, do we get the correct walk-off? And so we measured that, this walk-off, as a function of the angle of incidence, and we found that in fact it was doing exactly what it was supposed to do. the remarkable thing is that this uniaxial crystal actually works out to all angles in principle. And in our observation, as far as we could go, there are almost no optics that work out to all angles. So it's actually replacing free space for all purposes. It only works for one polarization. That's the other thing I forgot to say. So that's another caveat. And then in my last can I go with 2 more minutes? Okay. So the very last part of my talk was the uniaxial crystal sort of showed that this was in principle possible, that we could manipulate light via its angle, and that we could do something interesting with that transformation, which is replacing space. But it wasn't particularly useful because it's only replacing space in glycerol. And also the amount of space that you're replacing was only about 20% of the thickness of the crystal. So it wasn't a huge amount. And so our original idea was actually to make some sort of structured medium that could sort of dial in this angle dependent phase shift that you wanted to just by designing the medium. So our idea was to use a multi-layer stack. So this is just parallel layers of different indices of dielectrics. But other people have actually at the same time come up with their own ideas about how to implement our spaceplate idea, which involve photonic crystals and so on. I won't go too much into these, but just to say that we again used some sort of optimization technique to design some things. We don't really understand our structure, but indeed it gives us the right phase. The other drawback is it doesn't have flat transmission, which is what you'd want for free space. So we design these stacks. We'll go into that, and then we test them. So we've made these with our partner Iridian. And the way we have to test them is because they're multi-layer stacks, we actually have to put them onto a glass. And I didn't tell you this, but glass actually is the opposite of a space plate. It actually means that you need more space in your system to form an image if you put in a glass piece. So now we have glass that's doing the opposite of a space plate, and then we have something that's doing a space plate, and we want to only look at this, right? So this is what we have. And so we have a blank glass that we measure what it does, we measure what this does, and then we subtract the two and we figure out what that does. So the glass is this nice red line. So this is again the walk off, how much it tilts this beam. The space plate plus the glass is the blue, and then we subtract them and we find that the walk off actually happens in the opposite direction that you would from the glass. It actually has a different angular dependence. So that's an example of what we did, but we did it for all sorts of different designs. And they work for different angular ranges, and the slope basically tells you what R would be, that ratio of how much space you're replacing to the space that your plate is taking up. And these plates they're multi-layer stacks, so they're only on the order of microns thick, like 10 or so microns. And so these are all the different designs, and you can see they have different angular ranges, and they also have different slopes there. So we showed that it worked. We also showed that it could advance an image, but I didn't have time to tell you about that. It didn't look as impressive as the other one, which didn't work anyway. But one I wanted to draw attention to was just to say that it's not actually all that small an effect. Our glass piece is about 3 millimeters thick. Certainly, if you had this in an experiment and you moved your beam, you would be able to see it. You would just see your beam move back and forth. On one of our spaceplate designs, the effect is so large that this 10 micron thick structure actually behaves like enough space, anti-space, to compensate for what the glass is doing. So now when you put this glass in and you tilt it, the beam stays still as you tilt it. So that's this red line. So the glass, and then the space plate, with the space plate, sorry, glass plus space plate, and then we subtract them, we get the space plate. But the main thing I want you to see is that as a function of angle, the center of the beam is not moving as you tilt the glass. So I have a little animation here that kind of shows it. It's not a huge effect over the range that we tested it, but you can see that this is the space plate with the glass, and it's staying relatively still, and the glass is moving to the side as we tilt it. So we kind of call this the chicken head effect, in the sense that the chicken head, the beam is staying still as we rotate the glass. So that's our name for that. This is unpublished. We just got these results a few weeks ago. And so I have other stuff to tell you, but I'll just point out that coming in full circle, that in some ways a space plate is the exact counterpart to a lens, because a lens changes the angle depending on where a ray hits it, the distance, the position it hits it at. And it keeps the position, at least a thin lens, keeps the position constant. Whereas a space plate changes the displacement of position based on the angle it hits at, and it keeps the angle constant. So it really is just the interchange of the two parameters there. It is kind of the counterpart to the lens that we haven't really had before, other than just through direct free space propagation. And even if you look at the phase, like the phase of a lens looks like this as a function of position. So it's a circular curvature. And then for a space plate, it looks like that. So it is also the counterpart in terms of that. Okay, and the last subject I knew I wouldn't have time to tell you about, but there's another way of doing this that we also were interested in, that we studied, that's doing it with holograms. Again, you can select each K, but I'll just skip that. And so finish by just saying that I've shown you how you can alternate between phase mass and position and momentum to create arbitrary spatial beam array transformations. And we've shown that you can do a full range of these unitaries, and we'd like to do now more beams to show that this works, and then finally start putting in quantum light and doing some of these interesting quantum experiments with this device. And then if you go even further and directly manipulate the momentum, which I wasn't even sure that's possible, then you can start doing transformations that are even more useful for things like imaging and things like that. So we have lots of ideas about that. That was just the first momentum transformation, the simplest one we could possibly think of. There's more interesting ones to do as well. And so we are also looking at new ways of manipulating the momentum, like those holograms that I didn't have time to tell you about. And that's it. Thank you very much.